Welcome everyone to the now 11th qmeets episode. We are very happy to have two absolutely distinguished speakers for today's topic, and that is multipartite resources and I guess mostly entanglement. Let me shortly introduce the two. So first of all, we have Otfried Gühne. He is an absolute expert in quantum information theory and has contributed a lot to the theory of entanglement. In particular, entanglement detection, quantification, but also steering, metrology, and more recently, quantum networks. I guess that some of you also know him for his reviews, for instance, on entanglement detection and his theoretical work in collaboration with experiments. For instance, when he was a PhD with Harald Weinfurtner or recently with Jianwei Pan. He's also working a lot on graph states and theory and characterization of quantum systems, for instance, tomography routines such as randomized measurements. And I have actually seen, Otfried, that you lately published something where ADS-CFT was in the title. So even stuff like that you are now considering. Otfried did his PhD in Hanover with Maciej Lewenstein and Dagmar Bruce on entanglement detection with uncertainty relations. He then became a postdoc in Innsbruck, where he founded a small group in 2008. But only 2 years later, he became a full professor in Siegen, where he built up the Institute for Theoretical Quantum Optics, which has currently roughly 15 members and is extremely active. Then on the other side, we have Nicolai Friis. He is also well known for his research on quantum information theory and computing, and is focusing, similar as Otfried, on detection, characterization, and certification of entanglement, with a strong focus lately on multipartite entanglement. He's also interested in foundational questions, for instance, in the context of quantum thermodynamics and also relativistic quantum information. I'm personally a big fan of his work on fermions and what this actually has to do with relativity. He's also contributing to quantum optics, wrote a review in Nature Reviews Physics on entanglement detection, and also had some nice experimental work together with Rainer Blatt and lately Yvette Fuentes. He studied physics in Vienna, where he was also born, did his PhD in Nottingham 2013, then, similar as Otfried, went to Innsbruck for a postdoc with Hans Briegel, but returned to Vienna in 2017. Since a few years, he now leads the Entanglement and Quantum Computing Theory group within the Quantum Optics and Information Division of the Atom Institute. What I also really want to highlight is that he's an editor at Quantum, so maybe some of you have already sent something and he edited it. Actually, for me, this is true. And a cool side thing I definitely had to mention is his website has one of the coolest URLs ever, and that is QuantiFacts. So we are really, really happy that we have the two of you today. And with this, I wish everyone much fun.
Okay, good. Well, thanks for the introduction. So I think the idea is, that I start. I will give some more overview, and then Nico will talk about some more detailed questions. So I don't know. So maybe I just go into the full screen mode. One sec. To see a bit nicer. Good. So I will talk a bit about multipartite entanglement or multipartite quantum resources, as is written here. Yes, so I will just give an introduction, and I should also say that please interrupt me at any point. Yeah, so if you have a question, don't hesitate to interrupt me and ask questions, whatever. Yeah, so in principle, there should be always some time. Good. So, this is my first slide, and this is just a small map of Europe. And the red dot is where I'm sitting. This is Siegen, which is maybe not so well known because it's a quite small city. It's somewhere in the middle of nowhere. Well, you can also say it's in the center of Europe, but you can also say it's in the middle of nowhere. And then if you zoom in a little bit, it looks like that. So this is essentially the city we're living in. And if you zoom in a little bit more, it looks like that, which is my research group. Actually, it's a little bit older picture, but many of the people are still active and partly now in different places. But yes, some of the works that I will present also have been done with some of the people on the page. Good. So what I will talk about, actually, I just have maybe 3 chapters or 3 somehow small steps. So first I will talk a little bit about the entanglement of 2 particles. Then in the next chapter, I will talk about multiparticle entanglement and introduce the basic definitions there. And finally, I will talk about the question, what is superactivation? But actually, I will not go into too much detail because this will be then actually Nico's talk. So let's start with some basic facts about entanglement. And I mean, okay, this is, I just show you some pictures. This is a picture of a lake close by, which is, yes, quite nice. So what is the situation for entanglement? So typically we start with some state that is shared between Alice and Bob. And then we can ask different questions about the state. And in the simplest case, we have something like a pure state. And then we call a pure state entangled, or we call it separable if it's a product state. So Alice has her state and Bob has his state, and I sometimes write it like this, like A and B, and sometimes just in one line, cat notation. And otherwise, this state is entangled. And of course, for pure states, everything is simple, yeah, because you can directly check whether something is a product state or not. But for mixed states, it's getting more complicated. And then the definition is uses so-called convex combination. So given some density matrix, you essentially ask whether this can be written as some convex combination of pure product states. By convex combination, I mean that this PI form a probability distribution. So you can say that the state, at least in principle, can be generated by a source preparing only product states with certain probabilities. And this can also interpret as that somehow entanglement cannot be generated by local operations and classical communication, meaning the following. So by local operations, you can just definitely generate the states AI and BI. And with some classical communication, you can agree on the probabilities of preparing these states. And that means that such a state, that is such a convex combination, can be prepared somehow by this kind of simple classical protocol. But then the big question in our field is just given some state, is it entangled or separable? And this is in general a very difficult question. So you can view it as something like a set type pictures. If you have something like the entangled, so you have the set of all states, and there's a convex subset that is separable states, and the remaining states are some of the entangled states. And we should be a little bit careful with this picture because this is actually in a very high-dimensional space, namely the space of density matrices, which means that, for instance, for 2 qubits, it's a 15-dimensional space. But sometimes these pictures help to get some understanding of what is happening. But in general, this question whether a state is entangled or separable is not solved. It's solved for small dimensions, but not in general. And actually, it's proven to be a hard problem. So now you may ask, what are the simple criteria to prove that any state is entangled? And indeed, there's one famous and simple criterion, which is the so-called PPT criterion. How does it work? So what is a partial transposition? So well, maybe you remember the original transposition of a matrix, where you just transpose the matrix. And you maybe also remember that this transposition does not change the eigenvalues of the matrix. And for a product space or for product operators, you can also define something like the partial transposition. If I make just a transposition here on Bob's side, this is by defined, you can then define it for arbitrary operators. And interestingly, this can change the eigenvalues. And this is actually the basic criterion. It just states that if a state is separable, then this partial transposition has no negative eigenvalue. Yeah, so we must also call the state in PPT because it has a positive partial transpose, or one writes this rho to be is positive semi-definite. And the proof is very simple because if you have a separable state, it can be written as some convex combination of these product states. And now it's clear what the partial transposition does. It just acts on this thing and this just is mapped to some other state, and then it still says positive. The interesting thing is that this criterion is already quite strong. So one can, for instance, prove that if you have two qubits or a qubit of a qubit, then this is equivalent to being separable. And actually, the proof is already a little bit more involved, but this was already proven by a long time ago by the Rodetskis. So let me give you an example. Let's maybe give you first a theoretical example that you understand what some of this map is doing. So let's assume that you have such a state that is something like a singlet state, and I drop now the normalization. So yes, for simplicity. Then you have to can write down the density matrix, and this looks in the standard basis like that. You have this 0, 1, 0, 1 term, and this coherence terms on the off diagonal. Now, what is a partial transposition doing? The partial transposition is actually flipping these, transposing these blocks. You can see this 4 times 4 matrix as consisting of 2 times 2 blocks. And that means here I have to flip the entries. So I have to flip here the green entries, which does nothing. But I have to flip the red entries too. And then the -1 goes in the upper corner. And so here the -1 goes in the lower corner. And yes, here again, this partial transposition does nothing. But you also easily see that now, because you have this -1 and this -1 so off diagonal, this looks like a Pauli Z matrix. Actually, this one here is wrong. It should be a 0. Sorry. And this looks like a Pauli X matrix. So it has an eigenvalue -1. And this means the state is entangled. Good. So far, so easy. It's just a simple calculation. Just to give you an example that it's sometimes not so trivial. This is in a paper which appeared in Nature, okay, already some time ago. Okay, and then I don't mention the authors on purpose. So they did some photonic experiment, they generated from some quantum dots some photons which they claim to be entangled. And then they show some experimental data, they present some density matrix, and they claim here density matrices have strong outer off-diagonal elements which associate with entangled photons. Yeah, that's essentially the claim of the paper, that this density matrix is entangled. Now, if you understood this example that I gave you before, I mean, what does a partial transpose do? Essentially, you have to flip these off-diagonal entries, you have to flip them a little bit inside. Yeah? But then you still see that the remaining gray diagonal entries are much larger than the ones. Yeah, so that means actually this matrix is PPT. Yeah, so there's, I mean, obviously the diagonal entries are so big that it's still PPT, which means there's no entanglement in this experiment. Yeah, and this is maybe just a small warning that this can be useful, and to know this criterion, and yes, that is really in this experiment actually it didn't work out, and actually there was also a comment in Nature that people complained about this, but later they redid the experiment and then everything was achieved. Good. Again, if you have questions, please don't hesitate to interrupt me. Okay, good. So how does it then look? Essentially, we have some geometry of the state space. We have, again, the separable states inside. We have the entangled states a little bit outside. There are PPT states, which are a little bit larger than the separable states. And the NPT states, which have non-positive partial transpose, they are entangled. Then, for the remaining thing, we also need the concept of entanglement witnesses. What is an entanglement witness? An entanglement witness is just some observable with a nice property that it has a positive expectation value for all separable states. So that means if you take this observable and measure it, and you get a negative expectation value, you know for sure that the state is entangled. And you can see that in this egg-like picture really as something like a hyperplane separating something. Yeah, and so that means that here you have this hyperplane plane with expectation of 0, and everything on the one side is detected as entangled. And there's some basic properties. Yeah, first, for any entangled states, you can really construct a witness. Well, let's put it like this: for any entangled state, there is a witness, but it's often very difficult to construct. You can somehow look for optimal witnesses in the sense that, for instance, here this witness W1 is clearly better than W2 because it just detects more. And yes, there are some basic facts. There's an entire theory about entanglement witness, but I don't want to go into too much detail, but we need this concept. Instead of going into too much detail, I'll just give you a simple example, again, for the Bell state. So we consider this Bell state again. which is just a single state. And now one can prove, or one can calculate, that a witness for this state is given by this guy, which is essentially the following. I measure more or less the fidelity, because this is an overlap with the pure state. And if this is larger than 1/2, then 1/2 minus this gets negative, so then the state is entangled. And in an experiment, you would measure it like that. You would, for instance, write down this witness in terms of Pauli operators. You can just see that this witness, something passing Pauli's, is given by this thing. And then you can measure just this Pauli's. You can measure XX, YY, ZZ. And here's some very old data from an experiment by the Weinfurter group, where they did this more or less for testing purposes. And then you see, get some outcomes in the sense that, for instance, the measurement of sigma x times sigma x has 4 outcomes, because it can be something like a plus plus, a plus minus, minus plus, and minus plus, minus minus. And these are the probabilities, and from this you can calculate the expectation value, and finally you get something like a expectation value that is clearly negative, and this shows that the state was entangled. Okay, good. Let's come to the basic definition about multipartite entanglement. Actually, this is some small castle, the pictures from a small castle close by, where we did the group retreat 1 year ago. Okay, so what's the difference in multipartite entanglement? The main thing, what you have to keep in mind, that for multipartite entanglement, for multipartite states, you have different types of entanglement. For instance, for 3 qubits, you can have the following scenarios. You can have something like fully separable states, where you just, Alice has a state, Bob has a state, Charlie has a state, no entanglement, completely boring, that's it. But then there are also something like intermediate scenarios, which are, for instance, like biseparable states, where you can say, look, in this state here, something like there's maybe some entanglement between Bob and Charlie, but there's no entanglement between Alice and the rest. So Alice is separate, but still there's some entanglement. But still, this is something like not the most interesting state, people would claim, because in this case, only some parties are entangled and some not. So you did not entangle all the parties, and that's why it's maybe not the most interesting thing. Then there's the notion of genuine multipartite entanglement, which just means that all the parties are entangled. And for instance, for 3 qubits, you can write down things like a ZZ state or W state, which are 2 nice states with interesting properties. Maybe Nico will talk a little bit more about them, but yes, so this is something like just 2 examples of states. And for mixed states, you do the same again. You do something like convex combinations of these different families. And then, well, here are some more examples. So for fully separable states, you have something like this. Examples that you have just set with some probabilities, you get the fully separable states. Biseparable states can be actually biseparable with different bipartitions. For instance, you can make, with a certain probability, you have entanglement between A and B, but then with another probability, you have entanglement between B and C. But yeah, still, this is all biseparable. And there are other states which are entangled, which may be formed from the W state or the ZZ state. Okay, again, this has some geometrical meaning. And this is now more or less this picture, where you can say, look, here I have all the states, and they have some the very boring states of the fully separable states. Then I have the biseparable states, and there can be, first you can have biseparable with respect to certain bipartitions. For instance, here there are states which are separate for Alice versus Bob and Charlie. So Alice is not entangled with the rest. Here Charlie is not entangled with the rest, and here Bob is not entangled with the rest. But you also have, as I given you an example before, you also have mixtures of these guys, which are now the green things, which are also biseparable. And then everything that is bluish in this picture is somewhat like genuine multipartite entangled. And it can be that it uses something like W states in the decomposition of ZZ states. And these are the different things like the W class and the ZZ class. I mean, I should be a little bit careful with this picture. Again, I know you see that there's sometimes some things where you have to be careful, because what is not so easy to visible in this picture, that you can have things like that the state is separable for any bipartition, but it's still not fully separable. So it's something like in the intersection of all these leaves, but it's not in this reddish set, which means, yeah, so there's some subtleties which are maybe not so easy to depict in this kind of field. Again, you can write on witnesses, yeah, which is just again trying to construct some hyperplanes which separate some part of the convex sets from the rest. Yeah, typical examples would be something like, again, like this fidelity witness that I gave you before. We take essentially 1/2 minus the jet z state. So if the fidelity of the jet z state is larger than 1/2, then the state is entangled. Good. If you want to derive some separability criteria, this is a little bit more difficult for the multipartite systems because you always have this problem with this different bipartitions. Yeah, because you have to, with the biseparable states, there can be mixtures of these different kinds of A versus BC, B versus AC, and so on. And this is not so easy. However, there is a trick which one frequently uses in this kind of business, which is using a certain kind of relaxations, namely the following. Before, I can look for the biseparable states. And these are something like I take a separable state with Alice with Bob and Charlie, separable state with Bob and Alice and Charlie, and so on. Now, if I can relax this because I know the separable states are also PPT. So I can consider states which are called PPT mixtures, which are of the same form, but I just don't require these guys to be separable, but I allow them to be PPT, which is a little bit a larger set. So this is a set of states that I can just define. And these are in this picture, I mean, the first states, the biseparable states are the blue states, and I just make these sets a little bit larger to the red things. And then I can increase everything a little bit and look at this set. Of course, I lose some states, yeah, because it's I'm looking at a larger set. But the nice thing is that the question whether a state is something like a PPT mixture or not can more or less directly be decided by a technique that is called a semi-definite program. Yeah, and in practice, actually, it's even very strong. So finding examples which are biseparable, of states which are biseparable, which are generally multi-entangled, but still PPT mixtures is not so easy. Yeah, so in principle, this is a way to extend the partial transposition to the multipartite case and use it as a different kind of criteria. Okay, so in the last 2-3 slides, I would just want to point out what is superactivation. And well, just to give you a very basic example, I mean, if you have 2 telephones, yeah, maybe one mobile and just on a classical telephone, I mean, they're useless. Yeah, I mean, very clear. One telephone is useless, so why should 2 telephones be useful? Yeah, I mean, as both of them are broken, you don't gain anything. Which means, in classical thing, you always have to say 2 useless things are also useless, meaning that typically, yeah, I mean, it's simple. Yeah, 2 things which are, yeah, you cannot use it. So, interestingly, in quantum mechanics, there are examples where this is not the case. And this is actually superactivation. For instance, one early example was the following. You can have 2 quantum channels, which are noisy and so on, and each of them is useless. The capacity is 0. So you cannot use it to send messages because there's too noisy. But if you combine them, you can use it. Then the capacity is strictly larger than 0. So this is an example where something like 2 useless devices can be useful. And this is something called superactivation. Yeah, that's something like, yeah, you can do something like with 2 useless things, you can do something. And another example, what has been established is a notion of for Bell non-locality. So there are states which are local, so they do not violate any Bell inequality. And if you take 2 copies of them, then you somehow violate a Bell inequality. Yeah, and sometimes this is a slogan that people say 0 plus 0 is strictly larger than 0. And more mathematically, this leads to the notion of tensor stability. So it's very the simple question. So if you have 1 copy of a state, it has a certain property. Does it also hold for 2 copies of the state? And well, this can be true or not. And well, for instance, for separability, it's like that. It's true if a state is separable, then 2 copies are also separable. For the PPT criterion is also true. If one state is PPT, then 2 copies are also PPT. But generally, if you go this does not have to hold for all the possible properties. And actually, for instance, it's also known that such criteria, which are so-called tensor stables, that have this property that if you hold for one copy and they also hold for two copies, they cannot actually detect so much entanglement in high-dimensional things, high-dimensional scenarios. For instance, it's known that for the PPT criterion, there are entangled states that are very far away from the separable states if you go to high dimensions. Yeah. And now the question is just, does it also hold for biseparability? Yeah, so biseparability also means it's something like a useless state, but then you can ask if I have two copies of a useless state, is it also some sort of useless? And actually, this is what Nico will talk about in the next 20 minutes. So with that, I can close. So as the main thing, what I told you is that, yes, what you have to remember from Nico's part of the talk is that there are different forms of multipartite entanglement. That the PPT criterion is a strong test of entanglement and can be extended to the multipartite case. And then there's this question that you have this phenomenon of superactivation, which you can just say that 0 plus 0 can be at least sometimes be strictly larger than 0. So with this, I want to close this part of the talk. And yeah, now I'm open for questions.
Thanks a lot for this very, very nice overview in first part. So usually we do 5 to 10 minutes questions now. Please raise your hand or just unmute yourself, and then we can see. I have seen a raised hand by the Gärtner group. So please go ahead.
Actually, this was a mistake. I wanted to applaud, but maybe someone has. Sorry.
No.
Do we have a question? No. So we'll keep thinking. Maybe something comes up.
Okay. Okay, so while everyone is thinking, let me actually start with a question. So toward the end, you have already described a bit how you can turn two useless things into something useful. Of course, the mathematical details is another story, but nevertheless, I would be interested in understanding better how this works for the first example you had, and that was the quantum circuit. So you talked about that you have two circuits that have too much noise or that have zero capacity. So how can you end up with something that has finite capacity then? How does it work?
Okay, roughly, you can understand it maybe like that of course, if you have two copies of a channel, you can insert more states. You can insert entangled states between these things, and you maybe see a difference in that. Maybe to give an intuition, maybe which maybe actually also not so surprising this effect occurs, is the lower example, the one with a non-locality. So what does this mean? So I have one state which is local, means it doesn't violate the Bell inequality. And this means that whatever measurements I do, I can write down some classical model for it. Now, if I have two copies, of course, then then Alice has more or less for this 2 qubits and Bob has 2 qubits. But then also Alice and Bob can make joint measurements on their both qubits. So essentially the set of measurements that I can do is getting larger. That might be that then I cannot write down such a local model anymore. Yeah, this is somehow one of the reasons why this can fail. That essentially, for instance, this Bell scenario, just for if Alice has 2 qubits, she can make something like non-local measurements on a 2 qubit, and then there's no classical model explaining this. And I think for the case of quantum channels, you can see it a little bit similarly. That if you have two copies of a channel, then there are other things, other possible signal states that you can send, and this may lead to non-vanishing capacity.
Okay, so much of the story is actually hidden not in the states in the lowercase or the channel in the uppercase, but rather what you feed in, so to say, and which measurements you perform.
Yes. Yes.
Okay. Thanks
So
for clarifying.
that's maybe giving some intuition, yes.
All right. Then let's continue with the next question. Gabriela, please go ahead.
Okay, so I have some maybe clarifying question. I'm not so familiar with this approach. And I was wondering, because you were describing this partial transpose to detect multipartite entanglement, is it to detect arbitrary level of multipartite entanglement? So also for 2-3 partite entanglements, or only as a witness for genuine multipartite entanglement? Or maybe this is like different approach. Maybe this is just like a construction of the.
So here, the main thing is really to write down something for genuine multipartite entanglement, because yes, one wants to somehow because this is at first sight at least the most interesting form where you want to really prove that all the particles are entangled. Yeah, and this is the main thing where it works well and so on. If you would, for instance, do I understand correctly that you want to, for instance, look for as four particles, and you ask whether you can write them as in separations of three groups? This is something what you have in mind, not bipartition, but something like tripartitions.
Yes, because some lower level of multipartite entanglement can be still useful, let's say, for quantum metrology.
I mean, probably you can, but it will be okay. You can for the making having something separated into three parties, you can make some PPT relaxations again. But there are also some criteria which are somehow look, for instance, directly for separation into three parties. But actually, it will be technically a little bit more difficult and maybe not such an easy as semi-definite program. Yeah, so I would say probably it works, but it's not straightforward.
Okay, I understand.
All right, then Frederic, please go next.
Thanks for the talk. I will maybe ask a little bit of an annoying question here, because if you go from bosons, for example, to fermions, you know probably that there's a discussion whether one should use fermionic negativity by Shapurian instead of the normal PPT, or also whether one needs to use superselection rules. And I was wondering if you have put any thought into it, how this multipartite entanglement with PPT might be extended to fermions.
Okay, well, the direct answer is no. I did not think about this. I mean, I noticed if you talk about fermion entanglement as well as bosonic entanglement, one always has to be careful in separating something, this kind of entanglement that comes from the symmetry, I would say, from the real entanglement, because you have a certain amount of entanglement that comes from the symmetrization of the wave function, but is a little bit just due to the symmetry or antisymmetry. And the rest is, I mean, yeah, this later rank or so. I know some older works about that. But to be honest, I do not, or having this thing, what is just on the slide about this PPT mixtures for fermionic things, I never really thought about this, I must admit. Yeah, how one can implement this.
Probably would be quite annoying anyways. Thanks a lot.
But I never worked much on fermionic entanglement, so that's fine. Yes, I know that.
Okay. Are there any further questions to Otfried? I take this as a no. So let's thank Otfried again for this excellent talk.
Nice.
And now it's Nicolai's time.
All right. Yeah, thank you very much also for having me, and thanks for the kind introduction that you gave at the beginning. Also, thanks to Otfried for introducing the topic. So there's a lot of things that now I don't have to explain in detail because Otfried already explained them really well. Yeah, so my name is Nico. I work at TU Wien at the Atom Institute. And yes, one of the topics I work on a lot is multipartite entanglement. And I just briefly want to give you a glimpse as similar to Otfried as to where we are based. So on this map, you see the city of Vienna, and Atominstitut is this strange like 50s, 60s style building with a reactor. It's actually a working nuclear reactor in Vienna. And on the left-hand side, you see my current team, a lot of cool young people that I'm happy to have the opportunity to work with. And you see some of the illustrations of some of the topics that we've recently been dealing with. And you see sort of in the middle below our group picture, there's this strange image, which is also featured in the advertisement for this talk. So I hope that on my last slide, I get to actually tell you what this is about and what this strange alien creature there has to do with multipartite entanglement. But let me first get to the superactivation phenomena that Otfried was referring to, and try to give you a bit of more intuition as to what is happening there, and a bit of an overview of the history of the development of this area. Okay, so as Otfried said, this is a situation where we want to consider multiple parties, but to really understand what's happening, let's quickly go back to two parties, parties A and B. And what the usual situation is that we have some source, and the source distributes some particles to these parties. Yeah, and we call, let's say, the parties receive some first system, let's say a photon each or so, and then the source will keep distributing states. So we have a second copy, we have a third copy, and maybe many more. Okay. Now in the bipartite case, if that state that we're distributing is separable, so useless in the sense of this broken phone that Otfried mentioned, yeah, then we can write it as this convex combination with a probability weight and then a tensor product of two factors for A1 and B1 here. Actually, I'm not sure if you can see the cursor of my mouse, but I'm trying to point with that a little bit. Okay,
We can
so
see it.
now if we look at the states of the other copies, they are of course also separable if the first one is separable. And if we group together the parts of these different copies that pertain to party A and party B, right, we see that we still have this tensor product in the middle here. So it doesn't matter how many of these separable states we distribute, we will not get any non-separable states out of this game. But if we go to the multipartite setting, so if we have a source that distributes, say, states of three parties, A, B, C, Alice, Bob, and Charlie, if you will, then we have this strange situation that there are biseparable states, which can be mixtures of states that are separable, but with respect to different partitions. Okay, so here in this very simple example, I've chosen one state that is a tensor product when we separate A1 from the pair B1 and C1. And then there's another one where A1 and B1 are grouped together in some entangled state, but C1 is separate. Okay, and now let's have a look what happens if we take two copies of such a state. Okay, and let's write all the terms one by one. So the first two terms in this tensor product of these two biseparable states, in these first two terms, we see we can still group together the A terms here in blue, and in the second term, the C terms here in purple. Okay. But if I write down all the other terms that appear in this tensor product, I will see that now I have these red contributions where I cannot separate any A, B, or C parties sort of together. Okay, so if I try to separate the A's out, the A1 is alone, but the A2 is grouped in this red object here. And similarly, if I try to, let's say, isolate the B parts, B1 is stuck in here, B2 is stuck in here, I somehow cannot get them to separate up in the right way. Now, me writing this down is, of course, choosing a very specific decomposition of the state. There might be another decomposition in which this would actually work, but in order to find out, we'd have to check. It's not as straightforward anymore as in the bipartite case. And so this is now what we take as the starting point for our investigation. We want to know what can happen here. Okay, so let's take a look at the state space. As with Otfried earlier, just recall that what we're looking at here really is just a two-dimensional picture of a high-dimensional state space. So it will not capture all the features that we might want to look at, but it will give us some information as to what is happening here, okay? Now, in this state space, let's say for 3 qubits, for instance, we can consider some family of states where we mix together a GZ state with some white noise, okay? And thereby, we will move in a line that connects the GZ state, a pure state on the outside of the state space, to a maximally mixed state that is sort of at the center and is fully separable. And you see, as we follow this line, which means that we're increasing this parameter P that we have here, we can move all the way from the GZ state inside into the state space. Right. So for these states, we can then look at certain interesting properties. Okay, there are two things we want to leverage. Firstly, for any n qubit state rho x, okay, and I called it rho x here because it's assumed to be in X form. So we have a density operator with elements only on the main diagonal and main antidiagonal in the computational basis. If we get a non-zero value of a quantity called the genuinely multipartite concurrence, right, then this provides a necessary and sufficient criterion for GME, for genuine multipartite entanglement. All right, and we want to combine this observation with the observation that if we take any two matrices, two density matrices now specifically, and we apply what is called the Hadamard map or the Schur product, okay, then this Hadamard product, what it will do, right, it will be a component-wise multiplication of the two matrices. So if you take two matrices that have only components in this X places, sort of in the diagonal and antidiagonal, then component-wise multiplication will not create elements that are non-zero that are anywhere else, okay? And this Hadamard map can actually be implemented via SLOCC, so via stochastic local operations and classical communication. And the important thing is that SLOCC is a set of operations that doesn't create entanglement. So let's have a look how we can combine that. Okay, so we have our white noise added n qubit GZ states, and they are in X form. Okay, then we have this Hadamard product, which preserves this X form, and we know we can implement it via SLOCC, and SLOCC cannot generate genuine multipartite entanglement from biseparable states. So if we now have a non-zero GM concurrence, then it detects GME for these states in X form, and we can now apply this to this logic of looking at several copies. Okay, so if we have one copy, the statement is very simple. We just note that, okay, if this GM concurrence of our state is larger than 0, then we know that our state is GME. Great. So then we can define a threshold value for P that we call P1. Okay, and don't mind what the specific form of this function is here. The point is just we have a threshold value, and this tells us where do the states in this family in this one parameter family start being GME as we move from the left to the right. We move outside of the set of biseparable states and we hit this threshold value. But now we can do this for two copies. So for two copies, we apply now this Hadamard map, and then we check the GM concurrence of the resulting state. And if it's larger than 0, again, we know our state is GME, and that gives us another point, another threshold value that is P2 now, okay? So this threshold value will now tell us where two copies of the state are GME. And you see that there is now this gap here, okay? But I'll come back to this gap in a moment. So if we do this for any number of copies, let's say K, we can define similarly the Hadamard map. Now we have to take K minus 1 iterations of this map applied to our K copies. So we always take 2 and 2 and 2 and 2 and just reduce sort of the number of these elements here until we have, oh, sorry, I'm jumping ahead. And that gives us another threshold, all right? And then we have this family of thresholds that go in principle up to infinity, and they move leftwards towards this intersection of these sets where the states become separable with respect to some partition. Okay, so if we look at this, we can formulate these thresholds in a quite compact formula. Again, the specifics of the formula aren't really what the interesting point is, but in this paper, the authors are shown here at the bottom. We realize that actually with these thresholds, we can now see that there are states where we can tell that a certain number of copies will be GME. And indeed, we find that all these biseparable n-qubit white noise added GZ states are what we call activatable. So many copies of something that we would consider useless, biseparable, suddenly is GME. Okay, and we were, of course, interested in understanding what happens there. So we thought maybe this has to do with the fact that when you go from one copy to two copies, immediately something non-trivial happens, but maybe that's it, okay? And so what we found explicitly is that all 3-qubit white noise added GZ states that are between two threshold values, 2 and 3, okay? There are some where we know that two copies are still biseparable. So if we were to move on the right to the right of this P2 threshold, we would know that 2 copies become gene E. If we're to the left of it, we know 2 copies are biseparable, but 3 copies become gene E. So we suspected that really maybe there are states for every number of copies that require that number of copies to activate. But still, our analysis up to this point was limited to this one parameter family. And we thought, well, maybe this is some special feature of this one parameter family. Can we test this in something that is a bit like more complicated? And so, as Otfried mentioned, one can check another form of entanglement, namely PPT entanglement. So entanglement that is not detected by the PPT criterion and therefore would also not be detected by the kind of PPT mixture criterion that Otfried talked about. And we constructed such a state. So we considered a family of biseparable 3Q trit states. So that means there are 3 of them, but each is a 3-level system as well. So it's already the dimension of the whole problem grows a lot, okay? And we constructed these states so that there is no distillable bipartite entanglement across any cut. So we only have PPT entanglement across every partition, right? And then we found that even for such states, we could show that 3 copies of such a state can become GME. So at that point, we had already this strong suspicion that maybe what we're looking at here is something generic. It's not that we happen to find this isolated phenomenon that only happens for certain states under certain conditions, but that there's something more generic happening here. But we had some very talented colleagues, Carlos Palazuelos and Julio de Vicente in Madrid, who beat us to the punch. And they indeed managed to show that our suspicion was indeed correct. Although we didn't have a proof, they managed to get a very nice proof for this, showing that indeed for any number of copies, there are states that require at least that number of copies for activation. Okay. And then second, maybe more importantly, that every biseparable but not partition separable state is indeed GME activatable. So in this picture I drew here, you can see that basically this orange sort of triangular shaped area here, these are all the states that are not separable with respect to any cut, but they're still biseparable. And all of these can be activated in some sense, okay? And their paper stated explicitly a condition that this would hold for all finite dimensions. So this got us back into the game a little bit, thinking, yeah, okay, but would this not hold for infinite dimensions? Is there something special there, or maybe not? And so we started investigating this in my team together with colleagues in Olomouc in the Czech Republic. And what we looked there, what we found there for infinite dimensions is that you can show actually quite generally that indeed the finite dimensional result, it translates to the infinite dimensional case. So it doesn't matter what the state space dimension is, still every biseparable but not partition separable state is GME activatable. Okay, but in looking at this problem, we discovered that there's something else here. Okay, so even though the main initial question was settled, the problem that you end up having is you want to know, how can I even detect this activation? I need to know how to detect GME, not just in one copy of the state, let's say that already has 3 parties, which, as Otfried showed you, that can be quite non-trivial already, but now you have several copies and the state space grows and grows, and you need to somehow find witnesses that detect the genuine multipartite entanglement. And so in doing that, in looking at that, we realized that when we specialize to the infinite dimensional case to the typical situation of bosonic modes of harmonic oscillators, there a criterion that is often used for this kind of situation is called the covariance matrix biseparability criterion, which you see here. So if you don't know what a covariance matrix is, never mind. The idea is basically that for certain states called Gaussian states, you can capture all that is relevant about correlations in a matrix of second statistical moments, and that you can write criteria that have to be satisfied by all biseparable states in a similar fashion as you can for density matrices, where you basically take the matrix pertaining to the joint state here, gamma ABC, and you compare it to this convex mixture. So the convex, because we have probabilities PA, PB, PC, and convex mixtures of matrices that correspond to states that are separable with respect to certain partitions. And then you check this positivity constraint here. and you know that this must be satisfied for all biseparable states. But until this point, it was believed that this would also be implying biseparability for Gaussian states. But this turned out not to be true, okay? So it's not necessary and sufficient for Gaussian states, which means you can find very strange situations. You can find Gaussian states that have the same covariance matrix as biseparable non-Gaussian states, but the Gaussian state has GME, even though its non-Gaussian kind of counterpart does not by construction. So somehow this messed a lot with our initial intuition, and this is also, I mean, one of the examples for why I find multipartite entanglement theory so interesting, because even after many years of dealing with these kind of questions, they keep surprising you. They keep hitting you at interesting angles, and then you go like, oh, I didn't see that coming, right? So yeah, these kind of questions then turned into the question of how could this be experimentally confirmed. As I said, the more copies we have, the more complicated, the more challenging it then becomes to find specific measurement strategies to actually check for GME. And so there were two experiments, one of which I was involved in and one of which Otfried was involved in, one with trapped ions, one with photons, that then demonstrated this GME activation phenomena independently of each other, where the experiment run in the team of Martin Ringbauer in Innsbruck in his ion trap was focusing more on the preparation of biseparable states in such a way that there was no way that you could sneak in any kind of resource sort of secretly by making sure that the preparation of these ions happens in such a way that you cannot have GME to begin with, and then showing that two copies indeed have GME. Whereas Otfried, maybe correct me if I'm wrong, but Otfried, the experiment that you were involved in, focused more on the distillation aspect. So the question, okay, if I have distributed now two such copies, can I act locally, like Alice, Bob, and Charlie locally do something so that they can go from the 2-copy level back to the single copy level to get, let's say, from 2 3-qubit states to 1 3-qubit state that is then shown to be GME. Yeah, and so these perspectives, these experimental perspectives, we then also tried to tackle together, Otfried and I, with our teams. And we were interested in the question, yes, so how can we actually go about practically doing this, okay? GME can be activated, yes, but how accessible is it? Can we practically do this easily, or will it become essentially impossible to check whether many copies of a state are GME? And so we looked at different techniques that could be applied and asked questions like how many copies are needed for activation in specific cases, or how can we detect activatable GME on the single copy level? So if we have many copies, the state space grows so much, can we compress things back down, for instance, by doing local projections? The Hadamard map that I mentioned earlier is one example for such a situation, so that you can make the GME also more accessible experimentally. And in this question was hidden the question, can activated GME be compressed to the single copy level in the first place? So basically, you start with two copies that are biseparable, so individually biseparable, but jointly GME. Now, if you do this compression back to the single copy level, will you be able to detect it, the single copy state that you end up with? Will you be able to detect it as GME? Okay, so I've tried to illustrate this compression a little bit here, yeah? And the investigation was actually really interesting and revealed a lot of interesting features. Otfried mentioned the GZ and W type states. And so what you see in this graphic that I'm showing here from this plot is, again, a special family of states, so-called 3-qubit GZ symmetric states, okay? And they are parameterized here by two values, X and Y. I've written them here on the bottom, but these details aren't so important. What's important is this triangle with this colorful triangle shows this family of states, a parameterization of this family of states. And in this blue area here in the middle, all the states are fully separable, so we know we cannot activate them. But the states in this green area, in these green triangles, they are these biseparable states that could potentially be activated. And indeed, we find that if we look at many copies, then you see that, for instance, starting with the red state indicated by this dot here, if you start taking more and more copies, you start moving outwards in the state space. And at some point, you hit a state that is indeed GME. But what's interesting to observe is that where are you moving? Where in the state space do you end up with as you add more copies? And it turned out that what you can get is you can move out in the state space, then you do this Hadamard projection. So you're back at the single copy level. And at the single copy level, you can then ask, oh, what is the equivalence class, the LOCC equivalence class? Is it a W type state or is it a JZ type state? And it turns out, well, you can reach either. So you kind of go around the usual restrictions from just looking at single copy LOCC. And that was kind of an interesting observation that this is even possible. But this third question in this row of questions here, can activated GME be compressed to the single copy level for all states? Here, the general answer we found was no. So we could really find examples where this compression using local projections is just not possible, meaning somehow there are states where, yes, activation happens, but it becomes hard to use it, hard to access this activation somehow. So, and with this, I'm coming also to the last kind of project I wanted to quickly give a glimpse on, which connects to this figure I advertised in the beginning. Namely, if we want to deal with these GME activation phenomena, we also have to worry about, well, how do we detect GME in a single copy? What are the techniques that will be usable, that are scalable in some way? And often in experiments, the problem is we cannot do full tomography. We cannot measure all correlators between any number of qubits. And so this is something that I looked a bit at with my team here and with collaborators at ETH and in Sherbrooke. And we asked, can we find interesting witnesses for GME that only require sort of few body measurements? And so for that, we focused on specific states that are called graph states, which are examples for highly multipartite entangled states. And these can be characterized by stabilizer operators that are called SI here. And then what we found is that indeed, if you start with states that are, let's say, close to, in some sense, in the state space, such graph states, you can find interesting GME and K separability criteria, some of which have been around for a while, and Otfried has developed some of these as well. But we tried to develop a new one, which is based on the following quantity. It's like a sum of expectation values of stabilizers pertaining to different vertices in this set, and then another sum of expectation values of pairs of these stabilizers. And then what I'm not showing you is basically what threshold values you have to compare that to, because that depends in some more complicated fashion on the specific graphs. But looking at these quantities, we were able to come up with witnesses that are quite versatile, because you only need a few measurements or measurements on a few qubits to check them. And in our simulations, they also were detecting a lot of states and detecting a lot of structure, because they cannot just check for GME, but for what's called K separability. So if you have more than 3 parties, you can check for more complicated structures. And it turned out that you see in this formula, there's this gamma parameter. So it lets you basically scale the weight between these two sum terms, okay? And that gives you a family of different witnesses. But it turned out that most of the usual states needed either the first term or the second term, but not both. And so we try to find states which indeed need both terms in some fashion. And these we then dubbed Cthulhu graphs. So if you're familiar with Lovecraftian mythology lore, okay, basically we had these graphs which consist of completely connected graph in the upper half, and then the star graph in the lower half. And we felt this looked sort of like a head with tentacles. So that's where this came from. So just you're wondering why we have strange alien creatures in our talk, that is why. And if you want to know more, I'd be happy if you have a look at our papers. Yeah, and with this, I'm sorry if I was over time. I'm not sure I was, but thank you very much for your attention. And I'll leave you here with a slide of my team. Thanks very much.
Thanks a lot, Nicolai, for this very interesting talk that contained all the details. Okay, so we now have time for further questions to Nicolai, but if you have a more general question to both speakers, please feel free also in this regard. Maybe I will just start again while you can think of questions. I have actually 2, one that is more physics related to both of you and one very technical. So let's start with the physics related one. You have basically shown us how one can transform, let's say, entanglement between a few parties to entanglement between much more parties. And I was just wondering, or how this is related. And I was just wondering whether, from the perspective of resource theories, this way of, let's say, preparing genuine multipartite entanglement is in some sense better or more optimal compared to other ways of preparing genuine multipartite entangled states. Do you know what I mean?
Yeah, Otfried, do you mind if I take that one? Okay. It's a very good question. I think this is sort of at the heart of this problem, right? So, I mean, it all depends a bit on your perspective and what you start from with what you have access to, right? So I think activation of GME is probably not a very good way of preparing GME if you set out with saying, I want GME, right? Then I would tell you, well, prepare that state you want, right? And I would try to give you a protocol for how to prepare this state without having to take multiple copies. Yeah. I see this GME activation phenomenon in two ways. One of them is it's a kind of recycling protocol, right? So you have if you happen to have something that is already useless, it might not be as useless as you think. That's kind of the first step. And this might come into play actually much less as something you want to actively use as a resource if you are into that, but that might actually be something that you should be aware of before you discard something, okay? Or before discarding the possibility that there are some correlations there that you might not be aware of, okay? The second part is maybe connected to the word resource itself. So we say resource and the word useless, for instance, but what do we actually mean by that, right? So in a sense, these activation phenomena, they tell us that maybe there's something not entirely, well formulated in what we are calling a resource in the first place, or what we call useful or useless. So I think the issue is simply we have to be aware of what are all the ingredients, and if we formulate how useful something is, we should also take into account that a single copy of something is not the end of the day. So it should reshape a little bit what a resource really is, and whether we should consider GME a resource. Is it a resource when we have access to a single copy? Yes. But if we have access to multiple copies, then we need to define our resources more broadly. And I think this is the takeaway message there.
Thanks a lot. That clarifies it extremely well. And I also definitely agree with everything you said. Okay, then I had a very technical question. So on some of the first slides, you were constructing this idea that you have this row X state, so only diagonal and anti-diagonal. And then you had some statement and two papers where Markus was on. And I was just wondering, this statement looked extremely strong, like that the genuine multipartite entanglement concurrence is non-negative if and only if, and then some other thing I forgot now. But could you maybe just give some intuition for why you can obtain such a strong statement? Is it really because you have such a structured form for the state, or?
Yes, in short, yes. Basically, this X form, it means that if you really think about what that means, is that you always have these 2x2 blocks that don't interact with each other, right? As you go more and more in, right?
Yes.
And so this allows you to really limit the options of what decompositions you can have there, right? And you can start solving things in a way that you just cannot do if there's any other non-zero elements anywhere. That's at the heart of it, I would say. I think Otfried is the one who actually worked much more with these with these GM concurrences and so on. But that's at least my simple understanding. You're basically choosing a family of states that is restricted exactly in the right way to be easy to handle. That's my impression of these X form criteria.
So does this mean that there are, let's say, related or similarly simple classes of states where you can find similar statements than for other measures? Probably yes.
Yeah, sure. I mean, in general, I think if you look at the developments in entanglement theory in the last 10, 15 years or so, basically, whenever you have really strong statements, they're usually connected to families of states with very high symmetry, right?
Yeah.
And that's usually the key ingredient. The second you have a strong symmetry somewhere, you can also do calculations really well. Like the other day, there was a very nice paper on like entanglement in generalized Dickey states, where also you have a high level of symmetry, and then you can make statements quite sweepingly about entanglement in all reduced states and so on. So because you can kind of carry this symmetry deeper and deeper. But that's kind of the leading feature, right? If you have a strong symmetry to begin with, I mean, it's a very physicsy way of thinking about problems, I suppose. Yeah, then you can make a lot of clear statements. And on the one hand, this is super interesting and helps you understand a lot of things on the mathematical side. But also, basically, the second you hit an experiment, all these assumptions go out the window, and then you have to use a very different approach because your states just will have components in arbitrary places, and you have to deal with that somehow. Which is also an interesting challenge to be fair.
I agree, yeah. Okay, thank you.
Small addition to that. So I agree what Nico said, but one of the nice things that for some states that is actually for this graph diagonal states or this X states, that these are local symmetries, meaning by local operations you can bring any state in this form. And that's a nice thing that, for instance, even if your state doesn't perfectly fit to the symmetries, you can still apply these local operations, get a certain state, and then you get a lower bound on the entanglement. Yeah, so that's actually nice. And for some symmetries it works, not for all, but for the X states it works, which is a nice thing. So even if your state is not form, you can still try to apply it. It gives you some lower bound on the entanglement.
Well, thanks for that addition. Okay. I think we now have a real hand up by the Gärtner group. So please go ahead.
Indeed. Hi, since you mentioned that both of you worked with these experiments, I was wondering now, it sounded a bit like, okay, if you have multiple copies, you can activate this entanglement, this GME, and I was just wondering, like, working with multiple copies, what are the experimental challenges? Because, for example, for photons, our experimental friends always tell us, if you have multiple single photons you want to interfere, they have to be really identical and mode matching in time and frequency and whatever. I think Mary is also here. She can probably confirm. So what were the main challenges for the experimental platforms you were working with, and how scalable is this actually if you work with multiple copies? Maybe you can say something.
Yeah, I mean, I guess we can say something about the respective experiments we were involved with. I mean, first of all, how scalable is it? I'm thinking about how to say this diplomatically, but not very much, right? So the problem is it gets very hard. You acting on multiple copies is tough in different platforms for different reasons. But I mean, in the ion trap, it's perhaps up to some point, right? Easier. I could say, well, we had like, let's say we have 6 ions in the trap. We could put 9 ions in the trap. We could put 12 ions in the trap. And then do operations jointly on groups of not 2, but 3 or 4 or so. And that's still, yeah, sure, we could do that. But the limitations then appear mostly in, well, the number of measurements we would have to do. We would have to define witnesses on that level for suddenly where the local systems are not 2-dimensional, but let's say 2 to the 3 to the 4 dimensional or whatever. And so you need more shots, you need more measurements, and this is where the scalability issues come in, probably also before you even hit the point as to how many ions you could squeeze in the trap in the first place. So in our case, those were a bit the limiting factors to going to like the 3-copy scenario, because if you have 3 copies, simply the number of measurements and shots would increase. Let's say not catastrophically, but sufficiently much that it becomes less easy to do, I would say.
Yeah. Thanks.
Yes, maybe a small addition to the photonic experiments. I mean, the problem is also they do not scale. And then the problems occur that you just mentioned, that you have to make these photons overlap and so on. And yeah, for photons even difficult because there's this temporal difficulty. Maybe a small thing, I would say that such experiments are also, I would say, always proof of principle of maybe some distillation steps. Yeah, and this makes them interesting. But it's proof of principle. Again, it doesn't scale really up, but that's something really nicely that you can see this effect.
Okay. Thanks a lot. No more questions.
Okay. I see no further hands up, so I would say let's thank our two speakers again. It was really exactly how we want qmeets to be. And let me advertise quickly the next episode. Already in 2 weeks, we have Brad Leckie and Chun Yun, also going by the name Charles Cao, from Microsoft, talking about what they call quantum Lego. I actually still don't know what they mean by that, so let's see. All right, and with this, we wish you a nice evening and see you in the next episode. Bye-bye.
Bye-bye. Thanks.
Bye. Thanks for having us.
Bye.
Thank you.